Hi, I'm Paweł Spychalski and today let's talk about the PID controllers, or to be more specific about the D-term. What D-term is, what D-term is responsible for, and some other interesting aspects of so-called D-term that we are using in our flight controllers, like for example in the Betaflight or INAV, or to be honest, any other flight controller or just the PID control system. PID controller. If you want to know exactly what the PID controller and what are the parts inside of the PID controller, I do have a separate video, so today we will not talk about the PID. Today we only will be talking about the D, the so-called D-term. D-term. What is D-term? What D-term influences and how actually D-term is measured, and why this way of measuring the D-term brings us so many different problems. So let's begin with the D term. D in the name stands for derivative. Derivative, I hope this is the correctly spelled derivative. If you had derivatives during your mathematics classes in your high school or somewhere right there, you should be aware that derivative is the rate of change. Derivative is a measure of the acceleration. And for example, if we have a signal, here we have x, here we have y, that has a constant value, for example, the value is 7, then always the derivative of such a signal, so D equals how many? 0, because the derivative has value only when the original signal is changing. So instead of having a flat line, if we would have a line that goes like this and then like this, what would be the value of the derivative? Here is another interesting aspect of the derivative. Derivative can be computed at the point. So, for example, in this place, because the line is flat, the derivative, momentary derivative, is equal 0. Here, in the middle, when the signal is growing this side, when the signal is growing, then what will be the value of the D? Somewhere here between this point and this point, let's say it will be around 2. Of course, we do not know the x, so we cannot compute it in the better way. And how many is what's the value of derivative on this leg of the signal? Once again 0. So if we would put the D-term, the derivative, on the same graph, we would have a value like that. 0 goes to 2 for this period of time and then goes down to 0 again. This is very simple. This is very simple example where the derivative in this space of time, in this period of time, because x is in our case time, if we are talking about the gyro readings, it's a constant acceleration. If, however, the acceleration would be, let's say, not a constant, but would be changing, and instead of having such a nice flat signal, let me update our graph. So if we would have a signal, let's say, something like that, and then going up there quickly into different values, then the acceleration, once again, it would look like that. Here it would start also accelerating. Here would slow down, he would once again drop down to 0 because signal is not changing in time. Here it would fall very rapidly because you see it's a very rapid fall to the quite a low value over here. Here would grow once again for the 0 for this leg. Here once again would go pretty high. Then over here would drop again to 0. Here would be, because signal is constant, would be held at 0, and here would once again drop very rapidly, go high and be kept at 0 again. The first thing that you have to understand about the D term is that the derivative which is used to compute the D term in the PID controller does not only consist the frequencies that are inside of the signal of the measurement or the error or the set point, but D term can produce higher frequencies. Like here, the signal changed once, twice, but look, count how many times the computed D term changed. 1, 2, 3, 4. So we can roughly say that the frequencies inside of the D term will be roughly around twice as high as the frequencies in the original signal. But this is not only this one. Also the amplitude can be much higher, because the amplitude on the D term does not really depend on the amplitude on the original signal, but the amplitude on the D term depends on how fast the change of the original signal is. We can easily, so let me remove this part of the board. We can have a signal that has a very low amplitude. You see, we have something like that, but very steep edges over here, and we can have a signal that has a much higher amplitude and the mins and maxes of the signal is much higher, but because the D term is all about the rate of change, the D term of the first signal will be extremely high. Oh, sorry, no, this is wrong direction. This is the price you have to pay when you are improvising. The amplitude of the D term in this case for this signal does not really depend on the amplitude on the other signal, while in case of this signal, let's have it like that. Here we are growing, so we are having something like that. Here we go down to 0, and with the lower amplitude, something like that. I will not draw this line further because it kind of makes no sense. So this is why the D term on our drones always wants to fry your motors. Why? Because the output generated by the D term component of the PID depends not on the amplitude of change, not how fast you rotate around one of the axes, but of how fast the signal changes. And if the filtering on the gyro signal is not really perfect, because there can be introduced a lot of noise into the signal, because our signal will be looking something like that. Those small spikes over here that kinda are not really relevant for the gyro signal itself, because they do have very low amplitude, but because they are happening very rapidly, the D term on such a change can have much higher amplitude, and this can be fed to the motor. So, okay, we know about the problems with the derivative. Now, the question number one: how do we compute the derivative? It's a good one, right? Actually, the computation of the derivative is, to be honest, extremely simple, because we are not on our math classes when there are special ways to compute a derivative of the function. We are always working with the measurement of the signal when, for example, where the x, now maybe let's call it m, where m od n equals, for example, 7, m od n minus 1. That is the previous one, previous reading of the, for example, the gyro signal equals 6, and m at n minus 2, not 1, equals, for example, 6. We can compute a derivative in the present moment. That means if we are on the nth sample, then the derivative equals m od n minus m od n minus 1. And this is all. This is the only equation that is really used to compute the value of the derivative rate of change at any given moment. It's the current reading minus the previous one. And it's all. And the D term is the D as the derivative, as the value of the acceleration in a given moment, times kd, when the kd is the gain, it's just a number used to multiply the value of the derivative to compute the value of the d term that will be added to the p term and the I term and the ff term and all the other terms, and then introduced to the motor. So from the mathematical perspective, computing the d term is absolutely nothing super fancy, and to be honest, it's pretty simple because it's only one equation. It's current value minus previous value. Super. So at the sample n, the d term equals how many? 1, because 7 minus 6 is 1. Then at this period, at this moment of time, the value of the d term will be how much? 0, because 6 minus 6 equals 0. And this is more or less all. However, this is not the end of the story about the d term, and we have to combine this knowledge with the previously knowledge from the previous part of the video, when I told you that the amplitude of the derivative does not really depend on the amplitude of the original signal, but depends on the rate of change, how fast the signal is changing. And this also means that the frequencies in the d term can be slightly different than the frequencies in the original signal. This is why when we have d gains that are, let's say, high enough to have an impact on flight, we not only have to filter the measurement filter and then compute the derivative, let's call it d, but then before we will be able to introduce the derivative to the output, we have to filter this again with slightly different frequencies, slightly different cutoff frequencies, and usually slightly higher, and usually also more aggressive filtering to eliminate the spikes, high values that might appear and usually are appearing in the d term and the output of the d term, the PID controller, and are fed to the motors. And those spikes, those rapidly appearing spikes, because this is really a spike here and there on the d term. If you ever watched the black box log, you should know that the d term is indeed full of source spikes. If fed to the motor, can burn them. This is why the d term has to be additionally filtered. You do not have to additionally filter the p term, the proportional part, because there are no different frequencies in the p term comparing to the incoming signal, and definitely you do not have to filter the I term, the integral part, because integral acts as a finite, this is finite response filter, so no need really to filter anything for the integral. For the d term, yeah, you do have to filter the d term. That's not all of our adventures with the d term, because d term as a value can be computed from, let's say, different values. Now, the method number 1 is of computing d term from the measurement. What does it mean? When we are computing the derivative of the signal inside of the PID controller, we use only the value of the measurement of the gyro signal. We ignore the current set point if the pilot wants to make the maneuver, if the input value for the PID controller is changing. We are computing derivative only from the measurement. This has some, let's say, advantages and disadvantages. The advantage of such an approach is that there is no something called a derivative spike. I will explain exactly what derivative spike is in the next part, but derivative spike rather does not exist when the d term is computed from the measurement. This, however, has a penalty of the response of the PID controller always be, let's say, damped. There are applications, of course, when this is not a problem, but if, for example, we are into a rapid drone flight with a lot of fast maneuvers, then the computing the D-term only from the measurement has the penalty that the input, even if you move your sticks very fast, will be, let's say, smooshy and slow, and it's definitely not everybody expects. This is why, as an opposite idea, comparing to the computing the D-term from the measurement, you can compute it from the error. In case of the error, you compute the derivative, the rate of change, not the measurement, but also you take the stick input, the input to the flight controller into consideration, and you compute it from the error. Error as the set point minus measurement, and current error minus previous error gives us the D-term computed from the error. Advantages. The response of the PID controller is more rapid. Yes, there is still damping on the beginnings and at the end of the maneuvers, but also the stick, the set point changes made by you, by moving, for example, the stick, if we are talking about drones, have impact on the D-term, and the response is crispier, less swooshy. You do not feel like, for example, you are flying through the jello, because the movement of the sticks influences how much of the D-term is computed and fed to the motor. So the quad, because we are talking mainly about quads, responses slightly more eager to your comments. However, when you are computing the D-term from the error, there is something called the derivative kick, and the derivative kick is the moment. I will have to create another graph, and here we have the here we have time, here we have values, and the blue line will be the current set point, position of the stick. So let's say in this moment we move the stick like that. The red line will be response of the quad, the measurement of the gyro. Of course, it will be slightly delayed comparing to the input, because there's always a slight delay. And with the green line, we're gonna draw for us the derivative value. Because this is a constant value, then derivative is 0. Here, so what, the gyro is, let's say, relatively smooth, and the acceleration is never very rapid, when the stick movement is the very rapid. And because we are measuring the D-term from the difference from the very rapid movement on the stick and not so rapid response of the gyro, the D-term can have a high amplitude, which will, let's say, go out to somewhere here, and here it will start dropping, and over here will be, let's say, flat. This is called the derivative kick. When you make a rapid movement of the stick, the quad very eagerly wants to follow your movement, puts a lot of demand on the motor, and can, how to say it, jerk the whole quad. And the D-term kick in, the derivative kick in, is hard really to filter and can result in, well, let's say, not the best experience. This is why some of the people, well, maybe I will continue with a slightly different line. This is why modern flight controllers are really using different approaches to how to compute the derivative and how to leave the derivative, so that the derivative kick is not that much visible and does not affect your flight that much, and still you have good dampened response, the smooth response of the whole setup, and yet the movement of the sticks has the impact on the movement of your quad. So the first method is to use only measurement plus something else, plus something else. What is the else? This is a good question. Let's talk about the Betaflight, for example. Something else in case of the Betaflight is the feed forward. But bear in mind, the Betaflight feed forward is not really a feed forward. Yeah, it's using only the stick input, but because it's computing the derivative of the stick input, it's not really feed forward. It's the derivative of the feed forward, but somehow somebody in the Betaflight world forgot to say that this is the derivative of the feed forward, so they are okay. We will go to this later. So what the feed forward, or the derivative feed forward, or the INAV control derivative for the INAV 2.6, the next release is working. It's just computing the derivative of the stick movements, multiplies this by the gain, and adds it to the output of the flight controller. This is why the D-term itself is handling only the smoothness, the softness of the response of the actual flight, so that, for example, the end of the maneuver is not very rapid, but rather with this slow deceleration at the end, and also the acceleration is not very rapid but slowly starting. This gives the flow to the flight, but with tuning, separately tuning of the feed forward, you can actually increase the response when you start the maneuver, when you start to move the stick. Because of course the derivative feed forward, or the control derivative, once you move the stick to a certain position, goes back to zero and has no impact on the output of the flight controller. But during the beginning of the maneuver, the movement of the sticks, it adds up to the output and helps to have the more locked in, more rapid response of the whole setup. So this is the more, let's say, in the flight controller world, the more modern approach to the problem of having both nicely damped response and also nicely rapid response when you move the sticks. Second one that currently we have to call 100% legacy was using something called the D-term set point weight. It was the value. It was just a multiplier and a simple equation that when the D-term set point weight was at 1, then the D-term was computed from error, and if you were lowering the D-term set point weight towards the 0, the input of your set point of movement of the stick on the axis was lowered to be D-term computed only from the measurement at 0, and on the other hand, if you increase it above 1, then the value of the error was increased, and it was more about computing the D-term from the set point than from the measurement. But the problem with the D-term was that it was extremely hard to tune the D-term, and it was extremely hard to fight with the derivative kick in and to tune it and to have nice feeling. This is why currently Betaflight for like at least almost 2 years now is using this D-term plus derivative feed forward, which is not really a feed forward approach. And from the INAV 2.6, the next release of the INAV will also have D-term separately and the derivative of the set point, control derivative, computed separately to have best of the both approaches. And I think this finishes our D-term lesson 101, the basics of the D-term and the derivative, and what affects the derivative and what affects the different ways of working with the derivative. And that's all for today. Until the next one, bye bye.